Hello everyone, this is Vasant, a 9-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to solve a problem on fluid mechanics from midsem paper. In previous lectures, we already solved this problem, this and this one. In today's lecture, we are going to solve this problem. You can read over here. A thin disc 75 centimeter in diameter is rotating at 50 rpm. So rpm is unit for angular velocity. It is revolutions per minute. So it means how many revolutions it can do per minute. So the gap between the base plate and the disc is filled with oil of viscosity 5 poise. If gap height is 6 mm, find the torque acting on the shaft. So this is the shaft. It is rotating with some omega, and this is the disc plate and this is the base plate. It is fixed over here. So there is oil and with the viscosity value mu. So let us, if you observe from the top view, the disc will be like this. So here this is the axis and we are applying omega like this. Right. So if you take a element at distance r, the velocity at that position will be r into omega, right? So here at a distance r from the axis, at a radius r from the axis, the velocity of the plate will be r omega. That means the velocity of the particles attached to that plate will also have velocity r omega, because we assume no slip condition, right? So here the velocity of the particles will be r omega, and from here we also know that at the base plate the velocity will be 0. So the variation will be a triangle, right, from 0 to r omega at a distance r. So similarly at a distance r means we will have a circle, right? On that whole circle of radius r, on the circumference, the velocity at the plate will be r omega and at the base plate will be 0. So the variation will be a triangle from 0 to r omega. So if you take a small ring element at a radius r and with thickness dr, so the velocity at that position at the shaft will be r omega. So see, it is rotating like this. The fluid is like this. It is rotating like this. So it will apply some shear force, right? So that shear force we already know from the formula tau is equals to mu into dou u by dou y, right? So and this is for Newtonian fluids. I think you know about different types of fluid. We generally assume fluids as Newtonian. Okay, Newtonian fluid. For a Newtonian fluid, shear stress will be given by mu into dou mu by dou u by dou y. So at a distance r, we already know that distribution, velocity distribution will be r omega, and this will be height h. This will be the velocity profile, right? So this is linear. So d dou u by dou y will be slope of straight line. So that will be is equals to r omega divided by h, right? So d dou u by dou y will be is equals to r omega by h, right? So shear stress on the ring element will be tau is equals to mu into, that will be is equals to r omega divided by h, right? So what will be the force on that ring element? That will be given by tau into dA. So that will be is equals to mu r omega divided by h into dA. what is the area of the ring element? Ring element ka area dA will be is equals to 2 pi r into dr, right? How do you know? See, this has the circumference 2 pi r and this thickness is dr, so 2 pi r into dr will be the area. If you don't if you unable to understand this physically, so let us cut this cut over here. Then if you take like this length will be 2 pi r, right? Cut over there and bend it like a straight line, then it will have length 2 pi r and this thickness will be dr. So what will be the area? Area will be 2 pi r into dr. Now I think you understand how the area dA will be 2 pi r into dr for a ring element, differential ring element actually. So dA will be is equals to 2 pi r dr. So tau dA mu into r omega divided by h into 2 pi r dr. So df will be is equals to 2 pi mu omega divided by h r square dr. So what will be d torque? Small torque at the shaft because of this shear force on the ring element, that is at a distance r. See, the total force df will be at a distance r, right? So that will be given by df into r. So that is 2 pi mu omega r cube dr divided by h, right? So dt will be is equals to 2 pi mu omega r square dr divided by h. What will be the total torque on the disc? That will be integral d tau, that will be is equals to integration from 0 radius to capital R. So that is 2 pi mu omega divided by h r cube, sorry, r cube dr. Yes. So from this we get that total torque T will be given by 2 pi mu omega r power 4 divided by 4h, right? So that will be pi mu omega r power 4 divided by 2h, right? So total torque T is given by pi mu w r power 4 divided by 2h, right? So what is pi into value of mu? Let us put these all values in SI units. So it is given that value of viscosity is 5 poise. Poise is a CGS unit. Poisuli Ti is SI unit for viscosity. So 1 poisuli will be is equals to 10 poise, right? So it is given in 5 poise, so it will be is equals to 5 poisuli into omega. Omega in angular velocity is given as 50 rpm. We need to convert it into SI units, so that will be 50 rpm. That will be is equals to 50 into 2 pi by 60. So that will be given by 5 pi by 3, right? Omega is 5 pi by 3 in SI units. So that will be 5 pi divided by 3. And R is 75 by 2 into 10 power minus 2 whole power 4 divided by 2 into gap is 6 mm. So 6 into 10 power minus 3 meters. Okay. So from this it is 5 into 0.5 into 5 pi by 3 into 75 by 2 whole power 4 divided by 12 into 10 power minus 8 divided by 10 power minus 3. This will be 10 power minus 5, right? So let us calculate this value using calculator. So 5 into 0.5 into 5 into 5 into 75 into 75 into 75 into 75. Okay, this value divided by 3 divided by 2 power 4. 2 power 4 is 16 and divided by 12. So this value is, we got this value as 13,55383.905 into 10 power minus 5. We put all values we substituted all values in SI units, so we will get torque in SI units, that is Newton meter. So that will be is equals to 13.553838905 Newton meter. So this is the total torque on the shaft. So how this torque is generated? Let us discuss that. So see, you are trying to rotate the disc on the fluid. So when you are trying to rotate the disc, the particles which are attached to the disc are also the fluid particles attached to that disc will also try to rotate, because this disc will try to rotate that particles. So because of that, shear stress will the particles will the fluid particles will experience shear force, right? So because of that shear force, see, these particles will try to resist, right, because of their viscosity. See, the fluid will not resist shear stress under equilibrium, static equilibrium, but it can resist under dynamic equilibrium. Means while moving it can resist the shear stress, but while in equilibrium, means while it is in rest, it can't resist the shear stress. Okay, so because of that viscosity, they will create shear stress. Because of that, torque will generate. Okay, so with this, we end today's lecture. In next lecture, we solve remaining problems of this midsem paper. Thank you.